Welcome. This is Rob McLeod from the University of Utah and the Scientific Computing and Imaging Institute. This is another in our series of documentary videos that explain the use of UncertainSCI, our software implementation of tools needed to perform uncertainty quantification for a simulation. This particular video gets us into the actual application of UncertainSCI to a class of problems, and we hope will be useful to allow you to envision your research being supported by this type of software.
Yes, this is Jess Tate. So Jess is one of the senior developers for UncertainSCI, so he knows a whole lot about what goes on under the hood and how to hook things up to other simulation software as well. So he's going to talk to us a little bit about actually using UncertainSCI.
Yes, thank you, Akil. So today we're going to talk about UncertainSCI a little, right now we're going to talk about UncertainSCI in a little bit more detail about how you can possibly use it in your forward problems and your uncertainty quantification research projects. So our design goals when we were making UncertainSCI, our design goals were to make an uncertainty quantification tool that was numerically accurate, that was adaptable to many problem types, and interface with a broad set of tools, because you all use different tools to do your simulations. We wanted to interface with as many of those as possible, and we also wanted to have a simple API. And so that's what we were trying to achieve with UncertainSCI. And what, as Akil mentioned, UncertainSCI focuses, at least right now, exclusively on the aspect of uncertainty that he called parameterization uncertainty, or sometimes called propagation uncertainty, where you have input uncertainty, some distribution of your parameters, or maybe it's one of your inputs into your modeling pipeline, and then that causes some kind of uncertainty on the output. And so what UncertainSCI does, I'm still getting used to saying that over and over again. What UncertainSCI does is it interfaces with your modeling pipeline in a non-invasive way, as we discussed earlier, to be able to take this input distributions and provide output distributions. So I think one of the first things we want to do in explaining how UncertainSCI works is use a simple example. And so actually, Jake is going to do that right now. I'm going to hand it over to Jake, who is a grad student working with Dr. McLeod, and he has an example to show.
So yeah, thanks, Jess. And so I'm going to, Akil did a really great job of explaining all the math, and I'm definitely not a mathematician, so I'm going to explain this more from a perspective of a user and not a developer of the program. And walk through just a very simple kind of mathematical example that everyone should maybe intuitively have a prediction of what the uncertainty is going to look like, so we can compare it to how it actually comes out. And so as we walk through a few times at this point, we have some sort of model that we want to do uncertainty quantification on. And in all of our visualizations, we've tried to treat this model as a black box. And we have some modeling parameters that go into this model that we use to take the output. We also have some model assumptions and some parameter distributions, as Akil kind of described before. And we need to use these things we know about our model to then get interesting statistics like the mean output, standard deviation, quantiles, parameter sensitivities, and a myriad of other interesting statistics. And we're going to use these polynomial chaos expansion emulators to do so. So the pipeline, as I see it, is always we take the model assumptions, model parameters, and distributions. We use that to get some samples of the parameters from UncertainSCI. We run those through a model to get the outputs, and then we pass those into the rest of the PCE pipeline to then get our UQ statistics. And so this model f of x, let's go ahead and define a simple one real quick. We'll say that x is some real vector, and specifically we're going to specify it between negative pi and pi. And we're going to say our model function is just the sine of x. Now, if we were to just take this as it stands right now, there are no parameters, and so there's only really one model output, and it's just a sine wave, right? And so we have to parameterize our model somehow. And in this case, I've chosen 4 parameters of interest: the amplitude, the frequency, the phase, and the offset of this particular sine wave. And so now we have the model parameters and our model set up. Next, we need to assess what parameter distributions we want to use. And so this can be a very difficult thing to assess, but it's based on whatever literature values or whatever assumptions you know about your model. The simplest one would be to say, for all of the range of values that I have, I assume that the likelihood of my parameter existing at one of those values is equal, and so I'm just going to use a uniform distribution for these parameters. Lastly, after we have that, we need to assess any final model assumptions, and in this case, we need to define what the actual bounds of our individual parameters are. So for this first example, let's go ahead and set the parameter bounds like this. We'll say P0, which is the amplitude, is going to be between 0.5 and 1. We're going to fix P1 and P2 to just be a single value. So we're going to say that the frequency is 1 and the phase is 0. And then we're going to have the offset be between -0.1 and 0.1. And so what we should be expecting to see out of this UQ result is that P0 and P3 should should account for most of the variability in the model, and we shouldn't see any variability coming from P1 and P2. So after that, we then pass all this information into UncertainSCI, and it takes some smart parameter samples that it would like to use to assess and create these emulators. I think Akil already had all of the good visualizations for that. And then from there, we run those through our model and get the outputs. And here's an example of the outputs I got for that particular model. Now, because I gave it 4 parameters to sample from, even though 2 of them were fixed, it asked for a lot of different outputs. But this is a simple sine function, and so it was pretty easy for me to generate them. From this, we then pass those into the PCE, and we get some of our output statistics. So in this case, I'm plotting here, the blue line is the mean solution, and then these bands show ±1 standard deviation. And that makes sense, right? We're seeing that we're just kind of shifting the signal up and down and changing the amplitude, but we're not actually changing the phase or anything that would, kind of skew the signal to the left or the right. We can also then plot the sensitivities due to variable interactions. And as we can see in this pie chart, parameter 0 and parameter 3 are accounting for all of our parameter sensitivity. If we then plot that as a bar chart, we see, as we expected, parameter 1 and 2 have no effect on the model, and parameters 0 and 3 have all the effect, with parameter 0, the amplitude, having a higher effect, which makes sense, it had a higher range. So just to walk through one more version of this to see how it changes, let's go ahead and give all of our parameters some sort of meaningful range. And again, we're assuming uniform distributions of these parameters, just using these different ranges. So now we've set the frequency to vary between 0.5 and 1, and the phase to be between 0 and pi/4. Okay, so just like before, we generate samples and get our model output. You can see it's a lot more heterogeneous now. We then calculate our same statistics. We see that this is a different mean signal and a different looking standard deviation. And we see a lot more activity going on the sensitivity map, which if we plot it out as a bar chart, we can see now all of our primary parameters are having some sort of effect on the model. And also we see some interaction between, say, the amplitude and the frequency, and the amplitude and the phase, and the phase and the frequency. And maybe a little bit something between all 3 of these parameters. Right, and so that was just a quick example that you can actually find in the UncertainSCI code if you go download it. This is the simple UQ example that might be helpful to play with if you're first starting out learning about how to use this tool.
Okay, so yeah, we like to start with a relatively simple example to give the conceptual idea of how to play with parameters and what you might want to set in your UncertainSCI pipeline. And so Jake mentioned that the code that he was talking about that implements his example is in the UncertainSCI code base. It's on the GitHub repo. You can download that. Here is a kind of a shortened version of it, where it kind of shows how it might be implemented in this simple case. So we have things like the first set of lines is how we set what we call the index set, as Akil described it, and that takes things like the dimension, which is the number of parameters you want to vary in your UncertainSCI example. In this case, it's 4 because we have the 4 parameters of the sine function. And then we describe the distribution of each of the inputs. We're setting them all to a uniform distribution, which is the same as a beta distribution with alpha and beta set to 1. We also declare the order. As you see, we set it to 5, which is the polynomial order, the amount of variability in the polynomial that you could have for the polynomial chaos emulator. And you could set this to lower if you feel like you don't need it as high. And of course, the lower the order, the fewer number of samples you are going to need, as Akil described. And then once you have these 3 kind of inputs defined, you can generate your index set by using this function total degree set, and that helps us basically design an experiment as a sampling experiment of the parameter space. And so the next set of lines kind of declares the model that we're going to be running in this example. You have the x vals, which is basically the x range, or the domain of the actual simulation, the forward simulation, from minus pi to pi, and there's going to be 100 samples. And then the bounds of the parameter space that we're going to try. And you can see that although we set the dimension to 4, we're holding the 2 middle parameters constant. So this is actually the first example that Jake showed in this particular case. Of course, if you want to vary all 4, you just change those 4 ones in the middle to whatever values you want. And then once we have our bound set, we declare our forward model using this lambda function, and this is implemented in Python. So it's, we can of course help, or there's plenty of online resources. So you just declare a lambda function, which allows you to evaluate the function at various parameters, which is in this line is represented by the variable p. And then what we do is we instantiate the polynomial chaos emulator using this polynomial chaos expansion function. You input the index set and the distributions, and then you build the polynomial chaos emulator by just, in this case, passing in the model the lambda function. And so this is, maybe, hopefully this is not terribly foreign in terms of Python coding for people, but if it is, we're happy to help. We can walk you through. There are multiple examples on the UncertainSCI GitHub page that you could try, and you can more or less copy most of the examples, except change your parameters and change your distribution. So and change your model out, and it will work. It will work for a vast majority of cases. So once you have built your polynomial chaos emulator, you can do things like pull out the samples that it generated, basically the parameter samples, the experimental design that UncertainSCI has done for you, and it will also run the models, and you can get those outputs. But maybe more importantly is you can get the output statistics of the uncertainties, the output uncertainty, the mean, the standard deviation, and in this case, the global sensitivity. And there's this extra step to get the global sensitivity in which you list all the interactions that you want to obtain from UncertainSCI, from the polynomial chaos emulator. So if you want to look at this in more detail or play with it, you can, of course, download it. These slides are online, so you don't have to write down the link. You can, of course, download the slides and copy the link. So that's just a simple example of how and kind of a little bit of how the API is set up. We have basically just a little bit of information about the architecture, and we'll go back to some more examples and how to interface it with some other software. We have these kind of 3 bits of code. We have the class distributions, and we have distributions, which are, the types of input distributions you can find for different parameters and inputs. We have the UQ method, which, in this case is, in most cases, currently is the polynomial chaos emulator, but we also have Monte Carlo implemented. And then we have some utilities that kind of help bind everything together. And this is all implemented in Python and it's built off really common libraries such as SciPy and NumPy. And so it should be pretty easy for everybody to install. And if you've had trouble getting it installed or getting any of the examples running, please, you can tell us in the chat. We'll talk about it in the breakout sessions or in the break. We're happy to help you. We want to know how we can make this work for everybody. So let's talk now, though, a little bit more about the uncertainty quantification methods that we have implemented. So as I mentioned, we have 2 implemented already, polynomial chaos expansion and Monte Carlo. We are planning on implementing more at some point, but these are some of the most generalizable ones, and so that it will help. They go quite far in helping a lot of people, we feel. And just as a recap, for polynomial chaos, we have this function that we're trying to basically estimate the distribution of, we're trying to estimate the function using these expansions, and we do this using polynomial chaos. And Akil is much better at explaining this, but what we're trying to do is sample the space using smart sampling, and Akil mentioned how we do that. We try to use this more efficient sampling methods, and then from that sampling, compute the 4 problem outputs, and then build the polynomial chaos emulator. So within the polynomial chaos class, which is a class within UncertainSCI, we have a few functions that are the most important, probably the ones you'll probably see most often and interact with the most. So you have one where you set the distribution of the inputs, and that's you'll see this in all the examples. You have one where you generate the samples, and the most common and the method that we implemented is called WAFP, or weighted Fekete points, and it's basically an adaptive strategy to choose efficient parameter sets to run your model with. And then you have this PCE build function, which we'll talk a little bit more about in the next slide. And then the stats, which is also very important for you, that you'll interact with quite a lot. And then this last function, adaptive expressivity. This is a new function that we won't really go into too much today because we don't have time, frankly, but it allows you to adaptively choose the index set in the polynomial order. So let's talk about how we build the polynomial chaos. The API for this, for building the polynomial chaos emulator is got a few different options. We saw in the previous example, you could pass a lambda function to your input model. And this is after, of course, you set your input parameter distributions and the index set. But, in addition to passing the lambda model, you can evaluate the model, in a different function or outside of UncertainSCI even, or in a different environment. You can save out the model outputs and load it in to UncertainSCI and assign that to the polynomial chaos emulator and build it. Or if you want to do everything kind of asynchronously, you can save out both the samples and the model output and run everything separate and then combine them all back together for the polynomial chaos emulator. So next, we want to talk a little bit more about the stats that you can get out of UncertainSCI from our PCE class. Jake showed some of them. For instance, the mean and standard deviation, I think most people understand fairly well. Maybe a little bit less easy to understand are these sensitivities. And what we're showing here in this pie chart and what Jake showed earlier are the global sensitivities. Basically how we calculate those is, kind of dependent on which statistics you want to get out of UncertainSCI. The mean and standard deviation and total sensitivities are actually the easiest ones to get out. There's a straightforward function that you just call and it will return those values. The global sensitivity, like we saw in our previous example, requires a list of all the interactions you want to get the sensitivity for. And then if you want to get the median or the quantiles, you simply need to basically define quantile ranges, the number of quantiles, and the values of the quantiles, and then you can use NumPy's. Basically. You can use NumPy's functionality to get these quantile levels, and then UncertainSCI will spit those out for you, and you can use those, in any way you want. We'll show some examples later. And of course, the median is the middle quantile, or in this case, it's actually the first one that comes out of this function call. Okay, so let's talk a little bit more about the sensitivities, though, since they're a little bit tricky to understand for some people, especially like I definitely had trouble understanding this. For instance, here we see what Jake showed in his example. We have his two examples, one with 2 parameters, one with 4 parameters, and we see that the global sensitivities in both cases. And with 2 parameters, when we vary 2 parameters, we see that these 2 parameters are mostly the sensitivities kind of are mutually exclusive. But when we have multiple parameters, Jake talked about the interaction between the 2, and that's where it gets kind of complicated. One of the nice things about the global sensitivity that's important to understand is that the individual sensitivities of each of the contributions, and each of these interaction cases, either whether it's a single interaction or double or triple or whatever, all these interactions will sum to 1. And so that's an important thing to remember. And also another thing that may be helpful for people is that this fraction of the sensitivity is going to be a ratio, which is going to be a fraction of the total variance of the solution. So when you have the standard deviation, for instance, or the variance, which is of course the standard deviation squared, and you want to understand, say, of parameter 0 on the right side, you have this. You want to understand the variation of this contribution for right here. You would then multiply the total variance by this fraction, 33.5%, and that will give you the variation of this specific interaction. And the interactions, of course, are somewhat a little bit tricky, and maybe it's still a little confusing to you. I hope when we talk about it more, it'll start to sink in better. I know it took me several times thinking about it to understand it, and we're happy to answer any questions that you have about it. So that's one type of sensitivity that UncertainSCI outputs. The other type is called total sensitivity, and this is the difference between these basically is total sensitivity tries to isolate the sensitivity of the model due to each of the independent parameters rather than the interactions. So if you see in this plot here, this is a different example. It doesn't really matter what it is, but this would be the total and global sensitivity. And as you can see on the bottom is the global sensitivity for 3 parameters, and the top is the total sensitivity. And one of the things that might be helpful to understand is that the total sensitivity is the summation of all the global sensitivities that involves that particular parameter. So the bottom, of course, is the 0th parameter and the 1th parameter, and then the combination of the 0 and the first 2 parameters. And so the total sensitivity for the first dimension, or the first parameter, or the 0th parameter, as I said earlier, is is just a summation of these two global sensitivities. Likewise, for this second parameter, it's a summation of these two global sensitivities. So that this is a useful parameter. This is a useful statistic for understanding how much each parameter affects the outputs, output variability. Although it's not as directly, it's harder to directly relate to the variance as the global compared to the global sensitivity. And we'll have some, Sumi Intro is going to talk about some brain examples that will help highlight some of these differences. And we'll also talk about this more with some of the cardiac examples. Okay, so I just want to briefly explain some of the the distributions we have implemented in UncertainSCI. We have this list here: Gaussian, exponential, beta, uniform, discrete uniform, and tensorial, which allows you to combine a mixed set of the other distributions. Tensorial does, assuming that they're independent, as Akil mentioned earlier. And there's some main functions here. They're called very simply. You saw in the that one example, in the example we showed, it's just a single line. You just declare which type of distribution and the parameters of that distribution. And I think, if we think about them in the 1D case, then they're pretty easy for most people to understand. Although it's important to realize that these distributions are multivariate, so it starts to become a little bit more complicated. But you can think about them in the 1D case, and UncertainSCI will kind of handle the multivariate aspects in most cases. And so that's kind of how UncertainSCI fits in the overall pipeline. We want to talk about how we can interface with other software, and I have about 1 minute left. So I'm going to highlight some really specific cases very quickly. And these notes are going to be online, as well as, and these particular examples may not be on the in the GitHub repo, but they will be later. At least not right now, but they will be later. We're planning on adding these. We just haven't gotten them in yet. But this is kind of how you might interface with other software. So, for instance, if you have your modeling pipeline implemented in MATLAB, you can actually run UncertainSCI with MATLAB. Using the native Python engine in MATLAB. So what you do is in Python, you can instantiate the MATLAB engine, with a code set similar to this. And there's more information about about that Python interface on the MATLAB site. But then what you do once you have MATLAB running, or you could do this, you basically set up your forward model, which in this case is fairly generic, but one of the important parts is this middle line where it says results equals, is here. Hopefully you can see my screen. Let's see. Oops, accidentally went forward. Where it says eng.eval run forward for UQ param. This is a model. This run forward FWD for UQ is a function implemented in MATLAB. And so what it's doing is this Python function is calling this MATLAB function and returning the result back to Python, which will then pass it back to, which will then run it in UncertainSCI. So it's got a few layers of interaction, and for more information about this, we can certainly answer specific questions. There will be, this example is going to be online, and you can look at that, and we can help you as much as we can. But then once you have this Python function, which wraps around this MATLAB function, then the rest is fairly familiar. You set up your UncertainSCI parameters and your distribution. You have the model, which here is again set up as a lambda model, lambda function, and then you build the polynomial chaos emulator using, in this case, this is one of the sub-functions of the build PCE function. And then once you have the polynomial chaos emulator built, you can pull the statistics and actually pass them back to MATLAB using this workspace function. So that's kind of a quick overview of how you might interface with MATLAB. As an example, here's another more generic example of how you can interact with another software that may not have a direct Python interface. Some of these do, Ski Run and Carp, for instance, have Python interfaces, and so there may be more direct ways to interface with certain software. But here's a way you can interface with just about any software. You first set up your polynomial chaos emulator by basically just defining the input parameters and their distributions. And then you generate the samples and you save those to disk using, and in this case, we're using the scipy.io library to do that. And then once you have those parameters saved to file, you can define a function. This could be in Python, or you can run this completely asynchronously. You can do this in different software where you load those parameters, and then you run your model on each of those parameter sets. And all you need to do is save those the solutions to your forward pipeline to disk. And then what you do next is load in both the parameter sets that you ran, as well as the solutions for those parameter sets, and then run your polynomial chaos emulator using this API. And then after you do that, then all the rest of the statistics are available to you through Python and UncertainSCI. So I know that was very quick. I hope that was helpful. Here's just as a, but that's all the examples we have time for today. We're a little bit over time, but we're happy to answer questions. As we talked about before, we built this tool to help you and researchers in general to address your UQ needs, specifically for 3D modeling bioelectric field problems and biomedical applications. And we hope that you find this tool useful, and we encourage you to download the software and try it out and let us know if you have problems, if you have questions, or how it works for you. So thank you for your time.
Thank you, and we hope you enjoyed that seminar that gets us into the practice of using UncertainSCI in a class of problems that may be common to what you're conducting as part of your research. So we encourage you to read more, visit our website, and learn more about what UncertainSCI can do for your research, and reach out to us at any time if we can help you with your projects.